My name is Mojtaba Rajabi, and my work seeks to understand how rocks break and then apply this knowledge to various aspects of earth sciences and engineering.
Hello, my name is Andrew Gary, and welcome to Seismic Sound Off in-depth conversations in applied geophysics. In this episode, Mojtaba Rajabi discusses his upcoming Pacific South Honorary lecture, Present-Day Crustal Stress Across Spatial Scales. Mojtaba shares why it's necessary to understand the present-day crustal in-situ stress field, the impact of investigating crustal stress at different scales, and the causes and consequences of contemporary stress in the Earth's crust. He also goes over the concept of stress mapping and what his years of experience studying basins have taught him. Visit seg.org/podcast to register for Mojtaba's course taking place on June 9th. This episode is sponsored by Geospace Technologies. As a leading innovator and manufacturer of wireless seismic data acquisition systems, Geospace Technologies offers a series of seabed, wireless seismic data acquisition systems designed for extended duration seabed seismic data acquisition. Geospace is committed to setting new standards for quality, performance, reliability, and cost savings to E&P companies and marine geophysical contractors. And now my conversation with Mojtaba Rajabi. Your honorary lecture, it's called Present-Day Crustal Stress Across Spatial Scales. So what is the overall goal of your lecture?
Actually, the overall goal of this lecture is to show geoscientists and engineers that in addition to large tectonic forces that play major roles in the state of stress in the Earth's crust, there are a wide variety of other sources that control the stress at different spatial scales. So in order to better understand the crustal stress state, analysis of both local and wide-scale sources are required.
Why is it necessary to understand this present-day crustal in-situ stress field?
Actually, there are a lot of reasons for that. As safe usage of the underground is one of the major challenges for energy security and sustainability in our future. In this context, the knowledge of the in-situ stress offers important information for the management of georeservoirs such as geothermal reservoir, hydrocarbon, and underground water. There is also a pressing demand to find deep geological reservoir for the safe storage of huge amounts of carbon dioxide into the underground to move through net zero. And the present-day stress is a key parameter to assess how critical the stress changes are that we need actually to induce into the subsurface with engineering activities. Such examples are induced seismicity, reactivation of sealing faults, and subsidence to long-term depletion. And if I want to be more focused in one of the examples is the mitigation of induced seismicity or induced hazard. It's the distance of the in-situ stress state to a given failure criterion. And distance indicates how much stress changes on a pre-existing fault can be tolerated due to induced or natural process before failure happens or new fractures generated. So there are a lot of reasons, and as knowledge of stress has numerous implications, various economic, scientific, and social aspects of human life.
Induced seismicity is something that I don't feel within the public conversation is as frequent as I heard a few years back. Is it still a really active scientific area of interest within geophysics?
And it's pretty active because with any types of injection or extraction or removing any material from the subsurface, there is a risk of induced seismicity. It's not just the injection of the fluid within the subsurface, even the extraction and even in the mining area, induced seismicity is really important, and it's going to be active science in the field for the future as well.
Interesting. The first thing that came to mind reading the summary of your talk was just the sheer scale of the task you were setting out to do. How is it even possible to explore these stress fields across the entire Earth?
That's a really great question. And I have to first clarify that the stress is not a single value. And I will discuss in my lecture that stress is a tensorial parameter and has 9 components. And over the past 4 decades, Several methods have been developed for estimation of in-situ stress at different depth interval. My lecture and actually my work is a part of an open access project named the World Stress Map Project that aims to help people to understand the stresses in the Earth's crust. So I'm a part of the World Stress Map team. It's a project with over 35 years of research on this topic, and it's still an active, ongoing project. So I've had this chance to learn from this project and then apply some of the findings in my research. So as a part of this project, we usually compile or maybe analyze the stress data from near the surface of the Earth's crust down to 40 kilometers using wide variety of methods, including geological structures, borehole data, focal mechanism solutions of earthquakes, and engineering methods that kind of analysis of the data in mining and civil engineering projects.
You mentioned studying the present day orientation throughout your talk. Do scientists have a decent understanding of the past stress orientation across the basins?
Well, honestly, there is not a yes or no answer to this question because when you ask about geological past, which in this case we call paleostress, you should be more quantitative. As you probably know, the Earth has had a long history, so any time step at any location through this long history could have a different paleostress pattern. So, similar to the present day stress, knowledge of present paleostress is also important because all the geological structures that we do see nowadays in the Earth's crust have been formed with the paleostress in the Earth's history. So, there are a lot of methods that scientists use to have an idea about the paleostress. So, and depending on the time and location, the answer to your question could be different.
That makes sense there. The end of the title of your lecture is across spatial scales. How does investigating crustal stress at different scales impact what you find?
Actually, to me, the analysis of stress in over 35 basins from across the world showed that large-scale stress analysis do not necessarily represent the in-situ stress pattern at a smaller scale. Similarly, the analysis of just a couple of borehole measurements in one area might not be a good representation of the regional stress pattern. But interestingly, all the stress sources acting from, I'd say, tectonic plate scale to wellbore scale are interrelated to each other, so that the in-situ stress at any given point in the Earth's crust is the result of all these forces and all different stress sources.
What are 2 to 3 causes and consequences of the contemporary stress in the Earth's crust?
In terms of the causes, or I'd say sources of stress, the major source of stress in the Earth's crust is plate tectonic forces. Then we have large intraplate stress sources such as large geological structures or lateral density changes in the Earth's crust, for example, topography. We then finally have a small scale source of stress, which are mainly geological structure at smaller scale. In terms of consequences, I'd say knowledge of in-situ stress has a lot of implication in different aspects of geology and engineering, and it really depends where the in-situ stress information is going to be applied. If it's, for example, for seismicity or earthquakes hazard assessment, if you want to inject or extract any type of fluid within the subsurface, if you want to store, for example, carbon dioxide on the ground, if you want to stop tunnel or mine from collapsing. So it's all about trying to understand how the fluid will interact with rocks and assess if they might break rocks or if they might collapse structures I mentioned, like mine, tunnel, or borehole.
What is this concept of stress mapping?
I'd like to first make a definition for the stress map. Actually, it's a map that visualizes a component of a stress tensor. It could be magnitude or orientation. And the stress mapping technique is a well-established method that, as I mentioned, it's been, in the early history of the stress analysis over 50 years ago, that helps us to have an idea about the state of stress in a region, and again help us to investigate the relative contribution of different sources of stress, from large plate scale tectonic forces to smaller scale to the local geological structures.
You mentioned that there's 34 basins you've been looking at. You've probably looked at many more in your career. What are some of these different stress patterns that you might find in studying different basins?
Actually, it really depends on the geology and tectonic setting of the basin. Stress analysis in several sedimentary basins shows that the state of stress in smaller scales can be very simple and consistent over large scale and suggests that present-day stress in these areas is directly linked to the far-field stress sources. For example, similar to the large forces that initiate at the boundary of the tectonic plates. But in some other cases, the state of stress could be locally varied and highly complex because of the interaction of different forces acting at different scales. So what I can say is that the stress state in basin is often influenced by a range of factors and not simply plate boundary forces or major intraplate stress sources.
Yeah. Would it be possible to predict the likely stress orientation or degree of complexity encountered in a basin?
My research in the past 12 years has highlighted the role of geology in the in-situ stress pattern of a basin. There are numerous examples that show stress pattern around geological structures could be perturbed. So if we have a decent knowledge about the geology of a basin, then we might be able to predict the possible stress orientation or even degree of the complexity. So I'd say geology play a critical role here.
Mm. Who is the perfect audience for this talk?
A good question. I'd say any scientist or engineer who works with the geological structures and the interaction between rock and fluid. So that could be a geophysicist who works with seismic hazard assessment, a geologist who works with tectonics and structural geology, or an engineer who deals with the stability of underground openings like tunnels, mines, or boreholes.
What is a question you hope attendees will ask themselves after your presentation?
That's a really great one. I'd say the question that I even myself ask after any of my talks. And the question is, how many borehole data in a sedimentary basin are required to have an idea about the regional pattern of stress in that particular basin? It's a really interesting and challenging question, I'd say.
That's a great one. And lastly here, a little bit more general, what principal teaching or point of view has helped you succeed in your field?
My research is all about geomechanics, and I did my undergrad in geology, then did a master degree in the application of geology in geophysics and reservoir engineering. Finally, I found that I'm a kind of scientist who knows about geology, geophysics, and reservoir engineering. That's resulted in a PhD in geomechanics. So, in my case, multidisciplinary knowledge, I'd say geology, geophysics, a bit of geodynamics and engineering, helped me a lot throughout my career.
Well, that's wonderful. I appreciate your insight into this talk, for staying very late in your part of the world. I will link to be able to register for your 2 talks. And the nice thing about this is you can catch it afterwards if you can't quite get it live. So thank you again for your wonderful insight and for putting this talk together.
Thank you so much for having me.
SEG produces Seismic Sound Off to benefit its members, the scientific community, and inform the public on the value of geophysics. To show your support for this show, please leave a 5-star review on Apple Podcasts and Spotify. Simply go to Seismic Sound Off on Apple Podcasts and Spotify on your phone. It takes less than 5 seconds to leave a 5-star rating and is the #1 action you can take to show your appreciation for this free resource. And follow the podcast while you are on the app to be notified when each new episode releases. Original music created by Zach Bridges. This episode was hosted, edited, and produced by me, Andrew Gary at 51 Features. The SEG podcast team is Jennifer Cobb, Kathy Gamble, and Allie McGinnis. Thank you for listening. This is Seismic Sound Off, signaling off.